Assume that there is a hot object suspended in a bigger chamber that's evacuated. So we have vacuum here. And the surrounding temperature, let's say the wall of this chamber is at room temperature. Now, what's going to happen here is this hot object will cool down and will reach to the thermal equilibrium with this surrounding. So it's going to lose heat here and will start to cool down and reach to the equilibrium. Now there is a vacuum here, and since there is a vacuum, we know that there is no conduction or convection happening here, and that represents another mechanisms for heat transfer that results in the emission of internal energy of object. So there is no conduction convection, and there is another transfer mechanism that involves emission of internal energy of the object, and that's why the object is just cooling down and reach to the thermal equilibrium, and that's what we call the radiation. Now, unlike the conduction and convection that we definitely need material or a medium material for the transfer of heat, radiation does not need the material medium, or in other words, it can happen in vacuum. So radiation is the only mechanism of heat transfer, is only heat transfer mechanism that also happens in vacuum. Again, this is unlike the conduction and convection, and that's the way that we receive energy from sun to earth. It occurs, radiation occurs in all sort of materials, in liquid, solid, and gases, and the energy transfer by radiation is the fastest. So transfer is the fastest, and it can be in the speed of light for vacuum or air. These are some characteristics of these radiations. Now, the other important part here is, let's say if you're standing by a fire at some distance. So this is me showing the. So let's say we have some fire going on, and you're standing at 30 degrees C, like the body temperature, and this fire could have the temperature of, let's say, 900 degrees C, and the medium between is air at 10 degrees C. Then what's going to happen? Still, we are going to receive the thermal energy from the fire. What does that mean here is this, the radiation heat transfer can occur between the two bodies separated, like the body and the fire separated by a medium colder than both bodies. So can occur between two bodies separated by a medium colder than both bodies. Now, this is unlike the conduction and convection. Recall that conduction and convection could only occur in the direction of decreasing temperature. This is another characteristics of this radiation. Now, what is the nature of radiation? Generally speaking, the way that we consider the radiation is the energy emitted by a matter as a result of changes in the electronic configurations of atoms and molecules. So radiation is, this is how we describe it: energy emitted by matter result of of electronic reconfiguration of the atoms and molecules. So that's radiation, and generally we call this reconfiguration and this transmit of energy electromagnetic waves or electromagnetic energy. Now, all electronic waves transport energy at the speed of light in vacuum, and the electronic waves are characterized by their frequency. We show it by nu and wavelengths lambda. And lambda, the wavelength of the electromagnetic wave is speed of light in that matter divided by nu, which is the frequency. So c is the speed of light, or let's put it as a propagation of wave. How fast the wave is just propagating in the medium that we are looking for. So in C is generally C0 over N, where C0 is the speed of light in vacuum, and it is 2.9979 10 to the power of 8 meter per second. So this is the speed of light in vacuum, and N is the constant depends on the material that we are looking. For example, N is 1 for air and most gases. Is 1.33 for water, and is 1.5 for glasses. So this is the way that we characterize the electromagnetic wave. Now, lambda is the wavelength, as we mentioned, and it has the unit of micrometer, which is 10 to the power minus 6 meter, and nu is frequency of the electromagnetic wave, and it has a unit of 1/2. Now, the frequency depends only on the source and is independent of the medium through which the wave travels. Now, we can also, there is another view that that was proposed by Max Planck in 1900, along when he was proposing the quantum theory, that we can view electromagnetic radiation as a propagation of a collection of discrete pocket of energy. Okay, so the electromagnetic radiation is the propagation of collection of discrete pockets of energy. And what do we call those pockets of energy? We call them called photons or quanta. So this is another way of looking at the electromagnetic wave propagation or radiation, that these discrete pockets of this energy are just like transferring and propagating in everywhere. Now each photon of frequency nu has the energy of, like, he defined that one too. So I would say each photon of frequency nu has the energy of, if we look at the energy of that, it's going to be a constant, the Planck's constant, times frequency, which is h, times speed of light in that matter, the matter that is traveling, and then divided by lambda. H is 6.626069 times 10 to power minus 34 joules second, and that's Planck's constant. So this is another view. One way is this electromagnetic wave is just propagating and transferring energy from the source that we are looking at, or this is like this discrete small pockets of energy that we're calling them photons, and that's the energy of each photon. Now, what you would notice here is the energy of the photon is inversely proportional to the wavelengths. Now, what does that mean? Short wavelengths radiation, something that you're familiar with, have heard of that, short wavelengths radiation, such as X-ray or gamma ray. They have larger photon energy, so they possess larger photon energy, and that's why they are highly destructive.